So let's go back to today's part. Okay. Yes. This month we have to think about some fundamental theory of manipulator. So how to calculate the manipulator position and how to calculate the manipulator joint angle. We have to think about. Yes. So it is the kinematics and the dynamics and we deeply understand about the direct kinematics. Yes, what is the kinematics? As I said previously, the manipulator is robot manipulator is basically, yes, this is blank and link joint mechanism, serially connected, link joint, and the end of this link, series of the link, some end effector is here, and by using the end effector, the grasping or some spraying or something, some hand tool is attached to the end effector and do some job. So therefore, we want to know joint space. What is joint space? What is joint space? Workspace なんですかね。What is workspace? そっちのワンさん。What is workspace? What is workspace?
The workspace is one joint moving all the direction that is limited to this
Yes, what is joint space?
joint space is DOF of the
yes.
joint that
Yes.
can move.
Yes, space. In this case, space means some parameters are variables. For example, this is sharp 1 joint is maybe theta 1 degree, and sharp 2 joint, theta 2 degree, sharp 3 joint, maybe sharp 3 degree, theta 3 degree, and so on. And joint, じゃあ次のタイランドの人たち。What is the end chips parameter? 3-dimensional space. What is in the 3-dimensional space? What is the end effectors parameter? Position parameter. What is the position parameter? End chip position parameter. What is the parameter in 3-dimensional space? X, Y, Z とそれから and theta 1 何theta 1 to 3まあいいや1 to 3でもまあアルファベータガンマとかまあなんかそういう yes 3 parameters for angular yes だからposition 3-dimensional position for example the px py pz and also for example the 3 rotational angle is a parameter in the 3-dimensional space yes 3 for the translation 3 for the rotation. So at least 6 parameters is there in the 3-dimensional space. So in this case, workspace. So therefore 3なっちゃった px, py, pz と例えばアルファ、ベータ、ガンマという6 parameters is there in the workspace. Okay? And yes, and also I have said this is a three-dimensional space of 6 parameters. So at least 3 degrees of freedom is necessary for the manipulator to do some task in the three-dimensional space. So therefore, the theta 1, theta 2, theta 3, theta 4, theta 5, theta 6 is at least necessary to do something in the three-dimensional space. So therefore, the joint space, joint parameters is for example the theta 1, theta 2, theta 3, theta 4, theta 5, theta 6 is a joint parameters. Yes? 1 by 6 vector. Yes, this is also the 1 by 6 vector. One by 6じゃねえや。6 by 1か。6 line 6 line 1 row ですか。6 line 1 row column. Yes, column. Yes. So the joint from joint to the end effector is here direct kinematics. Yes. Maybe it is easy. Yes, this is theta 1 is several degree, theta 2 is several degree, theta 3 is several degree, theta 4 is several degree, and so on. You can build up to calculate this part point to the position and also the direction. So it is easy to get. This is a forward kinematics or direct kinematics. But also the important is maybe you want to know. Yes, this arm is a manipulator. Yes, fixed to shoulder, and I want to pick up this. これ倒れちゃうんだよ。I want to pick up this pen. これも倒れちゃうな。ダメだ。Yes, pick up this pen. Yes, I want to grasp this. So this position and this direction is necessary. So how to realize this posture? How to realize this posture is we have to know. Yes, theta 1 should be some angle, theta 2 should be some angle, and also all of that angle is how to decide this angle is reverse kinematics. Yes, this end chip position and direction is upright, and then we want to calculate each joint angle is inverse kinematics or reverse kinematics. Okay, so both is necessary to control the manipulator. Okay. So firstly, I will talk about the forward kinematics because it is easy to understand maybe. Okay. Dynamics. Dynamics is yes. Kinematics is a static condition. Static condition. Yes. For example, the position. Position. Yes. When the theta 1 is some angle, theta 2 is some degree, theta 3 is some degree. And in this case, what is the position of the end chip and what is the direction of the end chip is a static condition. But yes, it moves dynamically. When it moves dynamically, some part, mass part or some damping part or some spring part is we have to think to produce some torque. Yes, torque and mass and inertia or something we have to think is dynamics. But here we don't focus on the dynamics. Maybe if you understand the kinematics, you can understand also the dynamics equation of motions. Okay. So let's go to the next description of manipulator configuration and movement. Configuration is some posture or some structure of the manipulator and the movement. Yes, there are several methods to calculate the kinematics, and mainly this homogeneous transformation matrix is used. Homogeneous translation matrix is 4x4 matrix, and DH parameter, Dynamic Hartenberg parameter is famous on this homogeneous transformation matrix. Homogeneous translation matrix っていうのは 4x4 マトリックスで4×4 マトリックスなんですけど、だからなんとかってこういうマトリックスですね。4x4 マトリックスです。ホモジニアスマトリックスっていうのは。で、ここの 3x3 part is a rotational part, and this part is a translation part, and others is 0001 です。is a homogeneous transformation です。だから 3x3 is a rotational matrix, and 3x1 is a translation vector it contains. So in here I will talk separately about the rotational part and the translation part. Yes, this is a vector style because it's easy to understand the meaning of the translation. Yes, homogeneous translation is very useful to treat not only the rotational part but also the translation part is treated at the same time, but it little bit confused about the meaning of translation. So I will talk about separately about the rotation and the translation. Okay? Maybe if you understand about this vector method, you also can easy to understand this homogeneous 4x4 matrix, DH parameters. Yes, to do this, firstly, you should recall about the vector operation and the differential operation. Yes, scalar variable is ABC, looks like this. And the vector is yes, maybe you will write, yes, scalar is only, yes, this, and vector is sometimes this arrow sign is used, or the, yes, bold font is used to distinguish the scalar variable and vector variable. Okay, I hope you should do that. When you sign the scalar, you should simply write this, and vector or matrix, vector is here, and the matrix is yes, A is A matrix, looks like this. Okay. And also, I hope you should write, for example, this is a element number, 3 line, 1 column, or for example, 3 lines, 3 columns, you should write. Okay, because yes, maybe you can understand this is 3x4 matrix, 3 line, 1 column. T is a transformation. The row and line is the inverse. Yes, sometimes it is used to write to reduce the line margin, line space, and also matrix. The 2x3 matrix is 2 lines. 2 round and 3 columns, maybe you can understand. And operations, for example, this matrix product and this vector equal like this. Yes, this is 2x3 matrix, and this is 3x1 vector. So therefore, this production can be operated. So this looks like this. So and also you also know about 2x3 and product 3x1. So this number must be equal. 3 must be equal, and the result is here 2x1 matrix. 2x1 matrix. Yes, this is 2 lines and 1 column. Yes, maybe you can understand this. So yes, you should write B vector. B は one line, two columns. Yes, it's easy to write. And B1, B2 in here. And matrix 2 by 3 is the 2 lines and 3 columns. So therefore the operation, yes, you should write the operation. But it's easy. Yes, yes, here is here, and here is here, and this product is here. Okay, it's easy. Yes, next, the differential operation. Yes, when u is a t function, b is also the t function. How about this differential time varying function? Both function is a time varying function. And what is this? The differential t. これは別に簡単ですよね。この dt ビューと出てこれだけで。Yes, it's okay. And also, yes, next is this differential operation, angular varying function u, and time varying function c, theta. Theta is a time varying function, and u is a theta's function. Yes, what is this? これ別に簡単ですね。これは別に最初に yes, firstly, it is differentiated by theta, and theta is differentiated by t. Yes. So これ d シータ du とシータドットですね。Okay. ですね。じゃあ how about this? The differential operation 3, angular varying function, theta 1, theta d's function v. And time varying function theta 1, both theta 1 and theta 2 is a time varying function. What is this? This function is time variable. Time differentiated. What is this? Choose. What is this? What? It looks like this. So, but what? Both theta 1, theta 2, but yes, this is differentiated by ct. What is this? Yes, maybe you can understand that firstly, theta 1 is differentiated, and theta 1 dot, and theta 2 differentiated, and theta 2 dot. Okay. It's only the recall of some differential operation. Okay. いいですね。じゃあ next part is vector product. Vector product, and this is 3 by 1 vector p, and this is x is also 3 by 1 vector. So the vector product is here. Direction is perpendicular. Both p and x is yes, maybe the p and x. This product is like this. Yes, this direction. And the size of this vector is yes, this size of this vector, size of this vector, and the sine theta. Theta is angular between the p and x. Okay, this is only simple vector product. And the scalar product is only the component production, v1, v2, v1, v2, v1, v2, v2, and this is the size of the vector, and cosine theta ですね。Yes. And the vector triple product looks like this, is this equation. Scalar triple product is this equation. Maybe you should recall like this. Okay. Yes, this is used because sometimes the A, B, C becomes a XYZ coordinate systems unit vector sometimes. Okay, you should think about this. We will use it later. Yes, from this Cartesian coordinate system. When I say the Cartesian coordinate system, you should image. Yes, Cartesian coordinate system is a 3 axis, x axis, y axis, z axis. X axis, y axis, and z axis. And I ask you to image 3 coordinate system, maybe the x, y, z. And this is a unit vector. You should image x unit vector, y unit vector, z unit vector. So this is a O1, once, ice coordinate system. So xi, yi, zi. Yes, 3 unit vector you should image. Cartesian coordinates OY, Cartesian coordinates OY, origin is here, and 3 unit vector you should estimate at the right angle each other. Yes, of course. Xi, yi, zi is a unit vector. Okay? And also, as I said, the manipulator is a link joint system. Link joint system. Joint is, for example, joint is here. Joint link system. Therefore, you should think each link. Yes. What we want to get, what we want to obtain is this is a basement coordinate system. Basement coordinate system for O0, for example, O0. The x0, y0, z0. Here, and this is link 1, link 2, link 3, link 4, link 5, link 6, for example. Yes? And each link, for example, L2, each link, it has some local coordinate system. Local coordinate system is fixed to the each link. This is これリンク L は I-1 って書いてあるね。コーディネート I-1 でね。だからここは多分 O2 です。でそれで例えばここのリンク3だったらなんかジョイントのところ、ここのジョイントのところに何かリンク3あっちゃった。コーディネートシステム3 O3 is fixed on here. Okay. Each link. Yes, this is here is a basement, and some link is connected serially, and this is I-1 link. I-1 link with some base position has some the coordinate, Cartesian coordinate, x, y, z coordinate, but I-1 coordinate. And next link is Li. Li is here, and the coordinate OI is fixed on this link. Okay? So the base coordinate system, basic basement coordinate system is fixed on the ground, and each link has some local coordinate like this. Okay. Next. So for example, the rotational joint. This is I-1 link. This is ice link. Yes, here is a ice joint. Yes, this is the I-1 link. This is ice link. Yes, here is I minus 1's coordinate system, and this here is i's coordinate system. What happened here? This is rotational joint. So when we set it like this, it means coordinate is this I minus 1's coordinate is translated parallelly to here, and rotate around the z-axis. 変ですか? Okay. Transform matrix B とかで translated to yes. This is the origin position, but this origin position is moved to here, and at around here, around z-axis, it is rotated. Then this i's coordinate system can be generated, produced. Okay, parallel translation based on the link geometric structure. Yes, this is defined by link geometric structure of I minus 1's link. This is the transform matrix. And the transformation matrix A is decided with rotational axis theta 1. So in this case, this is around the z-axis. Okay. So this black ice coordinate system is around z-axis. It is a result of around z-axis theta I. So what is the relationship between these two coordinates? We want to know. So the next page, it is set. Next page. Yes, this upper figure shows. This is XY plane. XY plane, maybe you can understand. This is XY plane. So XYZ. So around the axis, it is rotated by theta. So from xi minus 1 to the xi is here. Okay. Rotate around z-axis. So what we want to know is yes, the result x unit vector is produced from this x I minus 1 and y I minus 1. Yes, this vector xi is this part plus this part, this x along xi minus 1's vector plus this vector. So here it is, the cosine theta I no xi minus 1 vector plus sine theta 1 no, this is the size of this vector, this is the size of this vector. Okay. Yes, it is also the same as the new y unit vector. New y unit vector is here. Yes, how to calculate this new y vector? New y unit vector is, yes, this is a x directions vector plus y minus I directions vector. Yes, from here. So the phi, this is minus sign, because this is the opposite direction, negative direction of this along this axis. So this is minus sine theta I here, and plus here the cosine theta. The size of this vector is cosine theta. Therefore, y is minus sine theta I xi minus 1 plus cosine theta y I minus I 1. Okay, and z-axis is the same. Z-axis is the same, so the new g is the same as the old g unit vector. So these three equations you can understand. This is a vector, okay? Vector. And all of these three equations is summarized like this. summarize like this. X, Y, Z, new X, Y, Z vector is by using this all X, Y, Z vector. Yes, this X path is this product here, and the new Y vector, unit vector is this product and here, and the new Z vector, unit vector is this product and here. So this is the same as this equation. Okay, this is 3 lines, 3 formulation, and this is a vector matrix formulation. Okay. So therefore, this part 3 by 3 vector, 3 by 3 matrix is a rotation matrix around the z-axis. Okay? Yes, here it is. Around z-axis, this 3 by 3 matrix is around z-axis. In the similar way, you can get this 3 by 3 matrix is around x-axis. This 3 by 3 matrix is around y-axis. Okay. Yes. And sometimes cosine theta 1 is written by Ci because it is the space consuming. So sometimes I will write this like this. Okay. Ci とか Si. This means sine theta I, cosine theta I. Okay. Yes. Yes, this is a matrix. A matrix is a B って書いてある。A. Here is a rotation part A. And the next page shows the B parallel transformation part, AB. So it means, yes, rotation part is A and translation part is B. Here, okay? And A to B, yes, mixed part is, it is said C here. ここに書いてある。A to B の combination, integrated matrix, 3 by 3 matrix is C. Coordinate translation at one joint link is C. Okay. But the B part, transformation part, when the theta, each position is the same,ここでなんだっけ、ここでこうなっていってこうなっていって、まあこうなんかこうなってるんだけど、3つ考える。これシータ1、シータ2、シータ3、シータ4、シータ5、シータ6とかあって、でなんかベースコーディネートがここにこうあって、ベースコーディネート O0 とかあって、ここにシータ1コーディネートがこうあってやっちゃった。O1 コーディネート、O2 コーディネートとかありますよね。O2 コーディネート、O3 コーディネート、O4 コーディネート、O5 コーディネート、O6 コーディネート。で、エンドエフェクターのところになんかエンドエフェクターコーディネートってありますね。O エンドエフェクターコーディネート。OB か O0 でベースと OB でもいいんだけど、OB コーディネートね。says several coordinates is here. This is OB, O0, O1, O2, O3, O4, O5, O6, O end エフェクターでありますね。フェンザスでパラメーターはシータ1、シータ2、シータ3、シータ4、シータ5、シータ6が6パラメーターですよね。6 by 1ベクターのジョイントスペースパラメーターですね。When all of this is 0、これが0の時、0ベクターの時には、0ベクターの時に、each coordinate is the same direction. When all theta is a 0, all parameter become 0, and all of these link local coordinate is the same direction. If it is the same direction, でここのトランスフォーメーションはeach トランスフォーメーションで A ファクターと B ファクターがあるって言いましたね。each トランスフォーメーションに A ファクターと A マトリックスと B マトリックスとあるって言いましたね。でこのコンビネーションが C だって言いましたね。コンビネーションは A と B のコンビネーションが C だよと。C、ね、でもbut when all these is 0 and this coordinate is the same direction, the B factor we can ignore B factor because B becomes a B3 by 3 matrix is 0 1 0 0 1 0 0 1 0 0 0 1というこういうマトリックスになりますね。So that we cannot think, we don't have to think B part, only the rotational part we should think on each joint. Okay? Soこの B パートはいらなくなりますね。Only the rotational part is AC become equal when we set this local coordinate is this, yes. All this joint parameter become 0. This is これなんて言ったっけ？なんたら姿勢、基準姿勢か。スタンダードイニシャルポスチャーとか、イニシャルポスチャー、スタンダードポスチャーとか、Yes。で、when the initial posture is these local coordinate becomes the same direction. We don't have to think B parameters, B matrix, only rotational matrix we have to think. で、さて、これが procedure of direct kinematics about position で how to calculate from joint coordinate system, joint parameter to the end chip parameter. Yes, this is a procedure to calculate the joint position. Yes, first step is understand robot structure, robot configuration. 構造ですね。What is a movable portion? Movable portion means a joint portion. Which direction is a rotational axis? You have to make clear. Okay? And secondly, ここに reference posture って書いてます。This is a なんか first posture とか basic posture とか reference posture. Set the reference posture. Reference posture means the posture appearance when all joint values are 0. For example, all links and joints are aligned on the line. Yes, in this case. Okay? When the all joint parameter become 0, it is a reference posture, basic posture, basement posture. And then draw the mechanical model, mechanistic model って書いてある。mechanical model, link joint model using the symbols. Yes, for example, yes, as I誰かできるかな。ファンさん。You remember the what is the シリンドリカルロボット、インダストリアルロボットっていうやつなんか覚えてる？あってシリンドリカルポスチャーロボットのこの3ベーシックディグリーオブフリーダムのなんか覚えてる？じゃあなんかスフィアコーディネートのスフィアコーディネートロボットっていうのを覚えてる？インダストリアルロボットにはなんかsome variety of the mechanical configuration and sometimes the cylindrical robot, sometimes sphere coordinate robot and Cartesian coordinate robot っていうのもあったよね。でそれから4番目がフォースインダストリアルロボットがアーティクレイテッドマニピュレーターとかいうやつだよね。覚えてる？ You remember this? シリンドリカルコーディネートロボットってどんなんでした？
上と下と
うん
動ける、
上と下と
それとこのハンドが回ること。
ここ回るんだっけ？ここが回るんだっけ？覚えてない。こうなんだっけ？あ、わかった。ここがこうなってここがこうなるんだっけ？ここがこうなってここが多分こうなってここがこうなるんだっけ？これ覚えてないな。
あ、これですね。
そうこれ上下があって違うだからこれごめんこれはみんな下がローテーションなんでこうだったね。下がこうなっていてこうなってこれがこうなったんですね。でこれがだから1番目のジョイントはローテーションで2番目のジョイントがプリズマティックジョイントで3番目のジョイントがこのプリズマティックジョイントでしたね。そうだから2トランスレーションで1ローテーションでどうやって書きますかって言ったらまあこうですね。例えばだから1ローテーションでベースローテーションでこのプリズマティックジョイントがあってでそれからこっちの水平のホリゾンタルプリズマティックジョイントがありますねっていうのがシリンドリカルコーディネートでスフィアコーディネートっていうのはこうなっていてこうなっていてここがプリズマティックでしたね。でカルテシャンコーディネートはカルテシャンコーディネートなんだから、全部3つの場所がなんかこうなってこうなってよく書かなきゃこうなって3つの3ディレクションに XY ディレクションに XYZ ディレクションにこの全ての方向にプリズマティックになっているのがカルテシャンコーディネートでしたね。でアーティクレーターとマニピュレーターはどうでしたかって言ったらなんだっけこうなってこうなってこうなってこうなるのが4番目のやつでしたね。というようにこのなんだサードパートドローメカニカルモデルジョイントリンクモデルっていうのはこういうのを書いてくださいね。You write this kind of model you draw this kind of model thirdly yes to draw this you should think you have to define the structure and reference posture. For example, reference posture. Yes, in this articulated manipulator. Yes, what is a reference posture? You have to set. What is theta 1 equals 0, theta 2 equals 0, theta 3 equals 0. Yes, for example, this is general purpose and this is a reference posture, theta 1 equals 0, theta 2 equals 0, theta 3 equals 0. Yes, for example, you can set here, okay, reference posture. And the fourth, set the local coordinate system on each link from base to end in order. Pay attention to origin position, the origin position of each coordinate system and direction of the coordinate axis. Yes. 次いきます。Yes. だからそれというのは今さ、例えば articulated manipulator about the articulated manipulator, yes, as you understand, this is a sharp 1 and this is a sharp 2 and this is sharp 3, yes, sharp 1, sharp 2, sharp 3 3 degree of freedom の articulated manipulator ですね here. And yes, what is the reference posture? What is the reference posture? You can think. Yes, for example, this is a reference posture of this manipulator. Okay? だから theta 1 equals 0, theta 2 equals 0, theta 3 equals 0 は yes, this posture, for example. And the fourth, set the local coordinate on each link joint. Yes, for example, this is a basement OB is here. OB is here, and this is link. Yes, O1 here. Yes, this is also O2. This is also O3. ON とか you should set coordinate system. Yes, this is a basement coordinate system, basic coordinate system. This is local one joint coordinate system, link coordinate system. This is a second local coordinate system. This is a third coordinate system, and this is the end chip coordinate system. If you want. Yes, you should write here. And also, what is this theta first joint do? To declare that, you should think what is the local coordinate axis. Yes, for example, you can set this is y axis, x axis, x1, y1. Yes, vector. And z1 vector is here, okay, for example. And the second joint, yes, this is also the z2 vector, y2 vector, x2 vector, you can set. Yes, this is also the z3 vector, y3 vector, z3 vector, you can, x3 vector, you can set, okay. Local coordinate ね。で、fifth, declare link vector on each link in local coordinate system. And sixth, describe relationship between neighboring local coordinate system. For example, rotation around the x-axis and telescopic along y-axis in order to understand coordinate transformation by each joint 書いてあるんですけど、じゃあ、what it means. Yes, you should set here, and what is the role of this joint? You should think. So in this case, this is around z-axis. You can understand maybe around z-axis. Yes, this is a rotation around z-axis. Maybe you can understand. And also this is a rotation, but it is a bending around here. So for example, this is around x-axis, for example. Yes, also here joint is this is around x-axis. Maybe you can understand. x3, x2, and this is z1 is important. Okay. So therefore, the relationship between the coordinate system. Relationship between coordinate system.これこれもう一回ここに O0 とこれが O1 とこれが O2 と O3 O エンドって書いてあるけど、でじゃあこのコーディネートベースコーディネートとファーストコーディネート What is the relationship between zeroth coordinate base coordinate 0じゃん B か B でもいいんだけどzeroth coordinateは base coordinate to the one's coordinate What is the relationship? Okay? これだからトランスレートとロテートだよね。だからparallelly moving and around the axis ですね。いいですね。parallelly moved and around the axis 違うそれだけ言えばいいんです。だから around the axisでしょ？違いますか？でこれ次に next the relationship the one's coordinate and the second coordinate what is the relationship between this? マーさん what is relationship? Translate and rotate around x axis ですね。だから、only around the x-axis, rotate around the x-axis ですね。Translate and rotate around the x-axis. So what is the translation between these three coordinates and these three axes? I want to know this local coordination system and this local coordination system relationship between these two coordinate system. Yes, this is a reference posture. Reference posture is here. Reference posture meaning that theta 1 is 0, theta 2 is 0, theta 3 is 0, theta 2 is 0. Yes, this looks like this. But basically, yes, for example, this is the basement and this is rotate around here. So this coordinate is not only translated but also around x-axis. So yes, これは多分 maybe it moves like this. For example, around z-axis, and here it is moved here and rotate around x-axis. For example, so it also rotate like something. So we have to think about this. So these relationship between these coordinate system is rotate around the axis, and the relationship between these two coordinate system is around x-axis, and the relationship between these two coordinate is around x-axis. Maybe you can understand the relationship between this isこれがfifth とか sixth この describe relationship between neighboring local coordinate is this task. Okay, you have to make clear which axis rotate around the x axis, rotate around the z axis, for example, you should make clear. Okay? Yes. これがさっきのなんか C マトリックスだから C01 マトリックス C12 マトリックス12マトリックス C32 マトリックスこれ23でも何でもいいんだけど10マトリックス23マトリックス So relationship between C matrix between the two coordinate systems it looks like this. Yes, by using this 3 by 3 matrix, so for example, by using this C23 matrix, we can understand the relationship between the third coordinate system and the second coordinate system. We can understand, okay? And by using this C10 matrix, 違う 21 matrix か 12 matrix か 12 matrix, we can understand between this coordinate system and this coordinate system. And also by using this C01, we can understand between this one's coordinate system to the zeroth or base coordinate system. So neighboring coordinate system we use this 3 by 3 matrix. 3 by 3 matrix, the contents of 3 by 3 matrix is, for example, the rotation around the x-axis. This is rotation around the x-axis, rotation around the z-axis. For example, yes. And also, when we set the local coordinate system, we can think this link vectorなんですけど、リンクベクトルはだから例えばこれはゼロスリンクベクトルですね。ゼロスリンクベクトル。これワンスリンクベクトル。これはセカンドリンクベクトル。This is サードリンクベクトル。サードリンクベクトルですね。それは何ですかって言ったらここのリンクに This is zeroth link, this is first link, second link, third link. Link has some vector ですね。でこれ L0 ベクトルだし、これ L1 ベクトルだし、L2 ベクトルで L3 ベクトルですね。ね。で L2 for example this L2 vector is here, L2 vector here, and so this is in local coordinate system. In local coordinate system, it's only the z component. でわかります？これのリンクにはこういうふうにリンクローカルコーディネート we define this is a local coordinate. 例えばこのリンクにこういうふうにリンクベクトルコーディネートシステムを we defined これ Z2 例えば Y2、X2 とか define しましたね。だからこのリンクのここのポジションのリンクベクトルはL2 リンクベクトルは何ですかって言ったら L2Z2 なんですね。だから only yes。ちょっと違うことにしましょう。これか。 言ってることはもうなんかいっぺんに済まそうと思ってるんだけど、例えばなんかこういうリンクこういうリンクがくっついてます。こういうリンクがくっついてますよと言って、でローカルコーディネートっていうのはなんかこういうふうに決まりましたね。今ローカルコーディネートこれが例えば2番目のリンクなんですけど、これy2 ベクターがこっちで x2 ベクターがこっちで z2 ベクターがこっちで、でここが O2 っていう場所ですね。 O2 で、これはこのリンクベクトルっていうのはジョイントのここからここまでのベクトルですね。ここからここまでこうベクトルですね。ベクトル、これを例えば L2 ベクトルとしましょう。L2 ベクトルとしましょう。で L2 ベクトルっていうのは何ですかって、L2 ベクトルはなんたら X2 ディレクションプラスなんたら Y2 ディレクションプラスなんたら Z2 ディレクションですね。generally expression. But in this case, we set like this. So only D2 component is there. So it becomes 0, and this is a link length is L2. L2 is here. So it's remaining only this. So the link 2 vector is the length L2, small L2, and only z-axis. For example. いいですか？いいですか？でこれも同じですね。だからこれも O3 っていうコーディネートシステムで、これ Z3 ローカル Y3 ローカルコーディネートシステムと X3 ローカルコーディネートシステムと、でだからここの場所からここの場所のリンクベクトルは L3 リンクベクトルですね。でだけどこれは長さが L3 のスモール L3 の Z3 ベクターになっちゃいますね。ね、例えば for example, yes, not necessary, yes, this part is 0, 0, 0, but in this case, and this is the pen, it is along this straight line, this position is along this straight line. It is the only z component is remaining. Okay. And then how to calculate the end chip position? So finally we want to know this position from this basement. From this basement. It's easy. これが例えば L0 ベクターですね。ちょっとなんか全然何も書けないな。これ L0 ベクター。これリンクの L1 ベクター。これリンクの L2 ベクター。リンクの L3 ベクター。そうだから例えばポジション P エンドチップポジションはどうやるんですか、ベースメントからどうやるんですかって、このリンクベクトル足すだけですね。サメーション of this four link vectors. Yes. So L1 プラス L0 プラス L1 プラス L2 プラス L3 のベクター足すだけですね。How to calculate the position of the end chip. OK? でも例えばこれはなんだっけ L0Z0 ベクターですね。これは例えば L1Z1 ベクターですね。これは L2Z2 ベクターですね。 これは L3Z3 ベクターですね。For example, it is shown in the local coordinate. これ generally, not only Z. Generally, it is L0 は例えばなんちゃら X0 足すなんちゃら Y0 プラスなんたら Z0 ベクターですね。これもなんたら X1 ベクトルプラスなんたら Y1 ベクトルプラスなんたら Z1 ベクターですね。Generally エクスプレッションだとなんたら X2 ベクターとなんたら Y2 ベクターとなんたら Z3 ベクターですね。G2 か。この L3 をなんたら X3 ベクタープラスなんたら Y3 ベクタープラスなんたら J3 ベクターですね。これ全部なんか it can written in the local coordinate ローカルコーディネートで書けますね、リンクベクターは。で、だけどでエンドチップは何ですか？ T エンドはポジションオブザエンドチップは何ですかって言ったら、これは L1 ベクター、L0 ベクター、L1 ベクター、L2 ベクター、L3 ベクターすべてをサムエーションしたもんですね。で、これはこうなんですけど、これはそのまま足せませんね。G0、G1、G2、G3 はdifferent direction ですね。different direction. So therefore we want yes. This is an expression by third local coordinate system. This is expression by second coordinate system. This is expression by first local coordinate system. This is expression by, yes, this is zeroth coordinate system. It's okay. So this expression should be translated in the expression in the basement coordinate system's expression. Okay, so this is a second coordinate system's expression, but it should be translated into the zeroth coordinate system's expression. We want to know all these link vector should be in the same coordinate system's expression to add each component. Yes, vector expression it's correct in the vector expression, but numerically we want to know the position of this end chip in the basement coordinate system. シュウさんわかります？このリンクベクトルはis yes, it's okay in the local expression. Yes, each local expression is okay, but to know in the basement coordinate system position. Yes, from here, yes, this position is when it. Now, presently, this end chip position is what we want to know. This vector. We want to know end chip position from the basement, so each link should be at. But numerically, when we want to numerically position, yes, this vector expression is okay, it's correct. But we want to know, yes, all these link vector should be expressed in the zeroth basement coordinate system's expression. So therefore, this translation matrix is necessary. Therefore, this translation matrix is necessary. Yes, this is the C matrix is a neighboring coordinates relationship. Yes, so therefore from O2, the what is O1? What is O1 is yes, this is here. From O1 to from O2 to O0, what it is? This is a combination of C12 and C01 ちょっとわかんないけど、まあいいや。C01, C12 is necessary to translate. Yes, from O3 to O0, from O3 to O0, this translation C Nissan, and also here C12, and this translation C01. Yes, three translation matrix is necessary from O3 expression to O0 expression. Okay. So that it is. So link 3 vector third coordinate systems expression to zeroth coordinate systems expression. These three matrix is necessary to translate in the basement expression. Okay, and also this second link vector, this is expressed in the second local coordinate system. From the second local coordinate system to the basement coordinate system, this C12 and C02, these two 3x3 matrix transformation is necessary to translate into the basement coordinate expression. Okay, only that. Yes, this is the seventh point. Develop transformation matrix from each local coordinate system to base coordinate system. It means. And third, add link vector from basement to joint position in order to calculate joint position. Add all joint vector from basement to the end chip to calculate end chip position. こんな感じですね。で、ninth, coordinate access direction of local coordinate system put on the end chip link through the end chip orientation 書いてありますか。まあいいですね。OK. Only that. And the remaining part I will only もう時間ないですね。Yes. もう時間なくなってきましたね。This is yes. I will explain later about only about the example. Okay? Yes, this example is first example is articulated manipulator, 6 joints. Yes. From this schematic writing, you should write firstly. Yes. First thing you have to do is make the model from this. Can you write the symbol? Can you write the joint symbol? Can you write this structure, this manipulator structure using some symbols?これ見てわかりますか? Yes. From this figure, you should write. Yes. This is like this. Yes. This is first joint. First joint is here. First joint is the rotation around here, and the second joint is maybe looks like this. Okay? Cylinder like this. And the third joint here. Third joint is also like this. Okay, and the fourth joint is here. Fourth joint is rotation around this axis. Yes, fourth joint is here, and the fourth, sixth joint is here like this. Yes, this is sharp 1, sharp 2, sharp 3, sharp 4, sharp 5, sharp 6. Yes, 6 degree of freedom joint is here. So, firstly, from this figure, you should write this kind of symbol expression. Okay? Symbol expression and set the coordinate 1 to 6 to set the axis corresponding during the reference posture. All theta is 0. We all become the unit matrix because yes, unit matrix is only this cross line is 1 and others it becomes 0. Yes. And yes, next is here looks like this. So this is reset. This is a reference posture. Reference posture is set along this line, and so on. Yes, this third part, fourth part, and this part. Yes, this is a connection, transformation, neighboring axis, neighboring joint, coordinate system. Neighboring coordinate system is expressed only C1, C2, C3, C4, C6. Yes, transformation. But from this point, from this coordinate to the base coordinate, you have to use this. Okay? From this coordinate to base coordinate, you have to use this. Okay? Only that. Only coordinate transformation. And it looks like this. And only that. Yes, this is, yes, today I will express only that. The remaining part I will explain later. And today's part is, yes, you should write this articulated manipulator, this order, as I said, okay? You should do that as much as possible. This part is the same as the previous page, okay? Only 1, 2, 3, 4, 5, 6, 7, 9 steps. As I mentioned in the previous page, okay? So you should apply this procedure on this articulated manipulator shown here, okay? Yes, most of them is written in the previous pages, so you should read it and you should write in order, in this order, as much as possible. Okay? Yes, self-learning by reading it. And yes, sometimes some estimation and sometimes more learning is necessary, but not so difficult. Maybe I have explained it completely. Okay? Only this is one example. Okay, you should write about this example. And I will explain next week about this. Okay? Yes, you should try to do that as much as possible by yourself firstly. Okay?